All right, so I'm not able to verify that the live stream is going, but I'm going to trust that it is. We're going to continue where we left off here. We got through fully all our linked list implementation. And what I wanted to do is I wanted to wrap it up with mentioning some variations on these things. So for example, you can also have what are called doubly linked lists, where it not only goes forward and you've got a concept of a next, but it also goes backwards, right? So that you can actually traverse both directions. And it would look something like this, if I can pull up my diagram properly here. There we go. So you can keep track of the head, but also you can keep track of the tail. And then you see that each one of these nodes not only has a next, but also it has a previous. Some of the things that we did in our implementation required us to stop short because we needed to get the previous value, and that means that we couldn't have worked back. And so we had to get the one right before, the node right before the one that we were interested in. But if we have a doubly linked list like this, we don't have to do that because we can, if we get that node, then we can always work backwards to the previous one, or we can work forwards to the next one. Now, you pay a price for that, obviously, because if you were going to insert something or delete something, now you've made your life twice as complicated because now you need to make sure that the previous one points to the next one and then the next one points to the previous one. You've got basically twice as many things to consider, right? So it comes out as an advantage, but it also comes at a cost, right? So it would be a design decision on whether or not you wanted to do something like this. I will mention that Java's linked list does, in fact, do that. It has a forward and a backwards. And then you also have something called a circularly linked list. Now, a circularly linked list is where you do not have a head necessarily or a tail. Instead, when you get down to the tail, it wraps back around to the head. And this allows you to do some things like circularly, so like everybody takes turns or something like that, like in a token ring network, if you've ever heard of that, really old school network where you connected all the computers together in one big circuit, right? Circle, because that's how the network worked. Of course, now we have modern routers and wireless, and you wouldn't do anything like that anymore. But it used to be that if you wanted to, have zero lag on all your gaming parties, everybody would bring their computer, and then you'd hook it up with, it was a coax connection, and everybody would hook it up so that there was zero lag because you were using the network right there. And that's how it worked. One computer would talk to the next computer, and everybody would get a token or a slice of network time on that circular network. So if you ever have a need for something like that, you can of course design it so that it wraps back around. You don't even have to keep track of a head at that point because there really is no head, right? If it's a circle, there's no head, there's no tail. You can just say that it's current, and then you're wrapping around until you get back around to the beginning, right? So that's a circularly linked list. You also have what are called unrolled linked lists, right? Let me show you the picture of that one. It's basically a hybrid, right? So that instead of each element containing only, it's a linked list, but instead of each node containing only one element, it contains an entire array of elements. In this case, I've specified that it contains M elements. This combines the advantages of both together. That is, some things are done in an array, so you have some limited random access, but also it means that you've also got the advantages of and disadvantages of a linked list. Right? It's kind of a balance between the two. Yeah.
So like an array of the elements have its own node.
Yeah. So yeah, what would it look like in our node class now? So our node class isn't just one element, now it's an array of elements, right? And that's the only difference, right? Usually you specify this M to be tunable to the memory system that you're using. So typically what you want to do is you want to reduce cache misses. So you've got this whole memory hierarchy where you've got disk, extremely cheap but very slow, right? Because it's a mechanical, hard drives basically. And then you've got main memory RAM, right, which is faster but also more expensive. And then you've got the memory on your actual processing chip. Super expensive but super fast. So this entire hierarchy here, you want to reduce cache misses. In other words, on the processor, if you're looking for a specific element in memory, it's not there, it's not loaded into the processor, which has limited memory, then you have to go out to main memory. If it's not there, then you have to go out to disk, to virtual memory, right? So you want to reduce the number of times that you're going down in this memory hierarchy because it slows things down, right? And what you can do is you can tune this M so that it fits perfectly into 1 page of memory, whatever that might be. If it's typically modern systems are 4K for 1 page of memory, so that you don't have to load up the entire array like in an array list. Instead, you only load up chunks at a time, right? And so this is tunable, and you get some of the advantages of both. You get some of the disadvantages of both, right? But it's a hybrid solution instead. You also have something called skip lists, and I've stolen this from Wikipedia. They had a nice diagram there. Think about a major city, right, and a bus system or a subway system or something like that. You have what's called the local, where at any station you can get to the next station, the next station, the next station, right? That takes a long time though, right? As we've already seen with the linked list, you always have to start at the head and traverse to where you're trying to get. But mass transit systems also have what are called expresses. So for example, if I'm at station 1 here, and I want to get to station 8, I could of course take the local, which is going to take a long time, right? And because I'm stopping at every single station. But what I could do is I could get on this express and skip station 2 and 3 to get to station 4. That'll stay on that express to get to station 6, skipping station 5. Now, that doesn't take me to station 8. So I get off and I get transfer to the local, and I go from 6 to 7 to 8, right? I got to 8 faster than I would have by taking the local, right? Now, of course, what you could do is you could draw every single relation, right? That's called a tournament graph. But now the number of connections, if you can go from any station to any other station, now it's way too complex because the number of relations that you have to diagram and have to maintain means that now everything slows down anyway. Because, yeah, you can get to anywhere that you want, but now you have to maintain all of those bus routes, right? Now you have to have 10 times more buses than you had because you need to support that many routes, right? Or in this case, 10 times more references in your skip list. So again, it's a delicate balance. You want as many relations and many skips as you can support, but you don't want to support all of them or too many of them because then you're wasting resources on the other end. All right, so those are some basic variations that we've seen. I'll tell you, one time I was trying to get back to the Narita airport in Japan from downtown Tokyo. I accidentally got on the local and I fell asleep. And 1 hour later, I was like, I got up and like, oh, I'm nowhere near to my destination here. And I look up and oh crap, I got on the local, right? And I'd only gone like a quarter of the distance that I needed to go, and I did not make that flight. So be careful of where you're getting on the local there, right? What we're going to do is we're going to look at 2 other types of variations here. One of them is called a stack, and the other is called a queue. These are list-based data structures. We'll start out with a stack, though. Have you seen stacks before? So maybe in Computer Science 1, right? Let's review what it looks like when you say build a program, right? This is the picture that I usually draw, right? So when a program gets loaded up, what you have down here is static variables, static memory. Then what gets loaded up is the actual program memory, right? The actual program. Then you've got main. We're just going to say that this is a C program. Now what happens when main calls a function? A new stack frame is created on top of this stack. Say that main calls foo, right? And that foo calls another function called bar. And that bar calls another function called baz, right? What these are stack frames. Stack frames. Right? And as function calls function calls function, we're building up, right? This is the top of the stack, and this is the bottom of the stack. Now, why do we like this as our program call stack? Well, what happens when Baz gets done executing? It needs to return back to the calling function. So what happens to this stack frame right here? It gets taken away, right? When function calls a new function, right? Let's say that Baz is now gone, a brand new one, biz, say that we call biz, is created, right? These are your breadcrumbs, just like Hansel and Gretel, right? How did you get to this call function to begin with, right? Well, I called foo, then foo called Baz called bar, or bar called Baz, right? This is why when you have an error in your, a runtime error in your Java, right, you get a stack trace. It tells you it happened when this function called this function, called this function, called this function. I think it actually works down. Or no, it works out, excuse me, right? And this is extremely efficient because all you have to do to return back to where you came from is pop this off the top, right? That's the operation, pop, right? What about creating something? You call this push, right? This is the call stack. Now, call stacks are going to be limited. Modern computing, usually you only have 4 megabytes in your call stack, right? So what happens when you fill this up and then you try to put something on top of it? Error, and we call that what? So it spills over the side. It's overflow, stack overflow, right? You make a, that's where they took the name from, right? It's just a stack overflow. Right? Now, what are we going to do? We want to create a stack to hold arbitrary objects, right? So I'm going to draw it like this, a lot skinnier here. Let's just go ahead and think about these in terms of integers, right? So suppose that I've got 42 here, good old Jackie, right? And I want to push elements on top of the stack and pop elements off the top of the stack. So if I'm going to go ahead and push 42, that means that it comes down here and that's what's now on the stack, right? Again, orient this. This is the bottom and this is the top. You are only ever working from one direction here, the top of the stack. This is just for visualization purposes, right? You can take your computer and you can turn it upside down and there's no top or bottom, right? This is just me saying, think of it like this, and we'll understand why here in a second. Let's go ahead and push Nico next. All right. There we go. I'm going to go ahead and push 2. Let's go ahead and push Justin Steele. There we go. And let's go ahead and push him on the top. All right. These are all ball players. If you don't follow baseball, fine. All right. So here's the push order. I pushed 42, 2, and 35. Now what happens if I start popping off the top? What's the first one that comes out? 35, right? What's the next one that comes out? 2. What's the next one that comes out? 42, right? So this is my pop order. Observe what's the difference between them. They're reversed. This means that you've got something called a LIFO data structure, a last in, first out data structure, okay? This is fundamentally different than what we've been doing so far, right? All right, so first of all, stacks are a data structure, right? Stacks are a data structure. Let's understand what we mean by that first of all, right? The key word here is structure. We like structure because structure can be exploited, right, for efficiency. So remember back to Computer Science 1, say, and hopefully you covered binary search. If not, we've covered it here before. Think about binary search. If I just gave you an array that was unsorted, right, is there any structure there at all? Not that you can exploit. There's a first element, a second element, a third element, a fourth element, etc. But there's no other structure that you can exploit other than random access. Now suppose that I gave you an array that was sorted. How can you exploit that to search? Binary search. You jump to the middle and you say, is that the thing I'm looking for? No. But that means that you can search in this half or this half. You've effectively cut it in half, which is extremely efficient. Because if you can cut something from 1 million elements down to 500,000 elements, down to 250,000 elements, down to 125,000 elements, right? You can get the job done super, super quick, right? That's structure that we like to exploit so that we have efficient algorithms. This up here is structure. in that it holds stuff in some way. But stacks are a restricted access data structure, right? In other words, look at the other things, right? Look at collections or sets. They're a bit unstructured. They just hold stuff, right? Sorted lists or arrays have structure. Right? You can exploit that that ordering for efficient search, right? Binary search, right? But sorting imposes an ordering on the data structures state, right? In other words, if I were to sort a list, I would be manipulating the state of its variables, of its values, and shifting them around so that now it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I would be doing that with respect to the state. A restricted access data structure imposes structure through the behavior, right? So that's different. A restricted access data structure creates structure through the object's behavior instead. And remember, what do we mean by behavior? We mean the public interface, the public methods. Right? We're going to restrict how you can do this. This is where the name comes from, actually. Right? Remember that if I just said stack, what comes to mind immediately? A stack of what? Fill in the blank. A stack of pancakes. I like that. All right. Something else that's usually circular is dishes. Right? Because all right. So here, but I like that pancakes. Sure. Let's go with pancakes. All right. Well, first, I guess maybe that's a bad idea because you've got that many pancakes. How do you eat them? You don't take this one off the top and just eat that one pancake, right? You just start cutting them in half and eating them in whatever order you want, right? So maybe that's not a great analogy. But if these were dishes, right? And I'm a terrible artist, so don't think that that's an accurate portrayal of dishes, right? But which dish do you take if you need a dish? Oh, the one at the bottom?
Yeah, check.
What are you going to do? All right, I'm just going to, just pull this out, right? Then what happens to all the dishes? They fall and they break, right? So the safe way is to take it off the top. Now you clean the dishes, right? Where is the safe way to put the next dish? On the top, right? This actually comes from old school cafeterias. I don't know if the cafeterias here are like this, but you have this mechanism where you've got a bunch of dishes and there's this little spring at the bottom, right? So that you can push a dish on the top and the spring goes down, right? And then there are these little clips at the top that will hold the dish in. Now you want to take a dish, you pop it off the top and these little clips make a popping sound. Pop, pop, they've got them at the Amazing Pizza Machine, right? You don't know, have you gone to the Amazing Pizza Machine yet? If not, then go ahead and head there sometime, right? They've got them at the Amazing Pizza Machine and they just... Oh yeah, it's for kids. It's only for kids. But no. You go to Iowa instead. All right, so you've got dishes here, and that's where it comes from. You push it on top, and then you take it off the top. We're not going to allow you to insert an arbitrary dish. We're not going to allow you to take away an arbitrary dish. What if you wanted that behavior? I want to be able to arbitrarily put something wherever I want to. I want to be able to arbitrarily take something out. That's a list. A list has an interface that would say, yes, you can put stuff in, you can take stuff out, you can update stuff, you can delete stuff, right? The basic CRUD. I don't want the basic CRUD here. I want to impose an ordering through the interface. And the way that I'm going to do that is by restricting what you can do, right? We restrict what you can do with the data structure. Right? Hopefully that makes it efficient. In particular, we only support two operations. Push, add an element to the top of the list, of the stack, right? And pop is going to be remove and return the element at the top of the stack. And again, I'm going double quoting here, top. Again, there is no orientation on it, right? It's just how you visualize it. So with that in mind, let's come over here and start designing that interface. Remember, we're going to go through this step-by-step process here, where we design the interface, we write some tests to see to set ourselves up, and then we go back and we implement the interface. Maybe that means that at some point we come back and we update the interface because we realize we need a way of doing this. We need a way of doing something differently, right? All right, I learned my lesson before. I am not going to just create a stack for integers and another stack for doubles and another stack for strings. I'm going to create a stack for whatever, right? Elements of type T. Again, how do I represent the elements? I'll come back to that. But what I want is a public void push, right? T element. Right? Why? Because I'm going to be pushing that given element to the top of the stack. Pushes, that is, adds the given element to the top of this stack. There we go. Come back later and actually implement it. Public T pop, right? So it's going to return an element of type T, and that's why I'm having the return type of T here, right? Removes and returns the element at the top of this stack. There we go. Give myself some room there. All right. Excellent. Those are the two basic operations that I want, and that's it, right? Would it be a good idea to add this one? Public T get element at the on some location, right? And then I don't know, index of element. Right? Does that sound like a stack to you? And I intentionally gave it a terrible name on purpose to draw your attention to the fact that this is breaking the interface. This ain't a stack. What is this? A list. You're shopping for the wrong thing. Go down aisle 5 where we sell lists, right? Yeah.
We now want to, in the pop function, add the parameter of the element that we want to pop off.
Well, it's always at the top of the list.
So it just pops
Oh, off the top of the stack, excuse me. Yeah, right. Pop some middle element. We don't want our dishes falling over and crashing, right? The data structure is what is imposing, we're imposing a restriction. No, you're only allowed to do these things over here. Again, if you want to do arbitrary things, go over there. That's a list, right? Let's come over here and create a stack now. Stack for integers. I'll just keep it simple. Stack is equal to new stack. And if I say, like I did in my diagram over here, 42, 2, and 35. So stack.push 42, 2, and 5, or 35. All right, there we go. I want to make sure that that works somehow. I could do a toString method, but this is simple enough that say that I just go in reverse. Print ln stack.pop. Right? That returns an element. What element should I expect if I pop out the next element, 35? Pop, pop. 2 and 42 are my expectations. Uh-oh, careful. What happens when you pop off an empty stack? Error? Okay. So, error. What else could happen? Null? Okay. Kill the program? Segmentation fault? Right? So we'll come back to that one. Again, this is a process by which my design will then inform my interface. Right? So we'll come back and worry about that later. Obviously, if I run this now, it's not going to work because this is not compiling. And so I need to actually implement these things, which means I need to now make a decision. How am I going to represent this stack? All right, well, yeah, visually. Top and a bottom. At the end of the day, it's a computer, and a computer stores stuff how? What's one way that we can store stuff? As a list, okay. And what types of list have we looked at so far? Linked and array. So let's think about an array solution here. There's an array. Where's the top? Okay, this will be the top over here. And so now pushing, what means what? I add something to the end, right? Popping means I remove something from the end. So if I were to add 42, then 2, then 35, it would look something like this. I need to keep track of where the top is, index of top, right? So that when I push something, what am I going to do? I'm going to say 37, right? I'll go ahead and put 37 in there. But then what do I need to do? I need to move this so that the index of the top is there now. What about popping? Say that I pop 37 off, right? And that goes out. I just move this index of top over. Right? I like that solution. Why did you immediately say the right side, though?
Because the add functions that already exist add to the right side.
Add to the end and remove from the end. I like that. What if we had been naive about it, though? And we said that, oh, no, we're not going to work from that side. We're going to work from the other side. Right? This is going to be my top. And so I push and I pop from here. Right? How am I going to add 37 now? Yeah, I'm going to have to shift everything down, make room for 37, and there we go. Dishes are going to fall. More importantly, there are only 3 elements here in this diagram. What if there were 3 million elements there in that diagram? You're going to be shifting 3 million things just to accommodate one, right? So if we went with an array-based implementation, we would have to be careful. Work from this end, not from this end, okay? For efficiency reasons. What's the other way that we've learned how to store stuff in a dynamic list? A linked list, right? I'm just going to assume that it's a doubly linked list so that you can go back and forth, back and forth, back and forth. Right, there we go. I'll say that this is, now where's my top and where's my bottom? Okay, but which side? The right side? Okay, the tail. I'll make this my top. All I need to do is work from that side. I can always add a new one and then just link this in, right? Just add a new one and link this in, link that in. Popping simply just means taking this thing and removing it. I can work at the top. It would be equally efficient to go at the other end. In other words, I could work at both ends with a linked list, and it's going to be efficient because all it does is involve creating a new node at either end. No shifting of anything here. So no shifting as long as you work at one end. No shifting as long as you, in either case, be working at either end. Let's make that decision now. How am I going to represent my stack? A list of elements, yes. Elements. Right. Now I need to instantiate it. Right. Let me go ahead and bring in list, import list. Right. I can go with do you want to go with a linked list, or do you want to go with a array list? Which one? Array? Okay. Let's go with an array list then. What would it mean now that I've got this list here? Right? What would it mean? I'm using Java's versions, by the way, not my versions. What would it mean, by the way, to change over to a linked list if I ever wanted to? One line of code. Right? Instead of a linked array list, I go to a linked list. Right? Okay. So now let's figure out what the push element means here. Right? Which you said array, so we want to work from what end? The right end, right? So this dot elements dot add element. Let me read the documentation to you because that's exactly what it does. It appends the specified element to the end of this list. Okay? So I'm working on the right. Okay? Pop. How am I going to remove the last element? This dot elements dot, there is remove, right? It's index-based, though. So how do I want to work at the beginning of the list? No, I want to work at the end, so this dot elements dot size, careful, 5 elements is 0, 1, 2, 3, 4, minus 1, good. Right? Now wait a second. Why just write a function that calls a one line of another function? Why don't you just use a list to begin with, right? Good point. This goes back to the object-oriented programming principles that we're bringing to bear here, right? Encapsulation, abstraction, inheritance, and polymorphism, something that is kind of like inheritance here, but we prefer it sometimes over inheritance. Let me ask you this question. A list versus a stack. If I did it like this in a UML diagram, right? This is inheritance. Is a list a stack? Is a stack a list is what I'm asking here. No, because what do you have over here with a list? Get element at an index, right? Insert at an index. And that doesn't sound like a stack to me, right? Because you're going to ruin your dishes, right? All right, well, maybe that's not the way to do it. Maybe a list is a stack. Is a list a stack? It adds functionality, but push and pop, right? It doesn't seem like, I mean, it's more restrictive up here. This actually kind of violates what's called the open-close principles. It doesn't really make that much sense to me. So these probably don't belong in an inheritance hierarchy, right? Instead, we prefer composition over inheritance. Do you remember talking about that? Right? Here's a prime example of that. I did not say extends a list because I wanted to be able to add elements and remove elements by pushing and popping. Instead, what I did is I used composition. Inside of this stack, we own a list of elements. Now we've got wrapper methods here that simply hand off responsibility of pushing and popping in terms of the list itself. From the outside world, do we see that that's a list? Can I say stack.add 100? Right? No, it's not, because it's not a list, it's a stack. Right? You can only do two things, push and pop. That's it. Right? So by making this public interface here, we have used composition over inheritance to get so that we don't have to repeat that work. Right? I didn't start off by saying, okay, I've got a private int or private t, right? Elements, and then private int size, right? Just like we did in our own implementation of an array-based list. No, I'm just going to reuse what we've already done, right? And control access through the public interface here. Right? All right, does it work? Let's find out. Remember, I would expect 35, 2, and 42. 35, 4, and 5, excuse me, 35, 2, and 42. All right, let's answer this question now. Does it error out? Does it return null? What does it do? I don't know. Index -1 out of bounds for length 0? What the hell does that mean? Indexing, I don't see any array here, do you? Right. Again, leaky abstraction. So let's go into that pop method and determine, right? If this list, or if this stack is empty, right? Do something different. Else I do this. Right? If this stack is empty, that sounds like a nice convenience function. Once again, my implementation is informing, oh, I need to make a change to the interface here. Because that sounds like it's a nice thing to have. A function that says if this stack is empty or not. Public Boolean is empty. Just like we had with a list, return this dot elements dot is there an empty? Is empty, right? There we go. I don't even have to check the size or anything like that. I just have a list, are you empty? If you're empty, then the stack is empty. Right? So if this dot is empty, I'll do something different. What is that something different? Yep, you said an error. Somebody else said return null. What if we return null? Return null. How do you distinguish now whether or not you pushed null onto the stack? And now you're popping it off, and oh, there's my element. I pushed null for some reason. Right? Do we want to support it that way? If not, then we need to come back here and rethink our push. Right? If you give me something that's null, then I'm going to throw it back at you. Throw new illegal argument exception. Right? Cannot push null values to this stack. Go design your own. Right? Then go ahead and pop. Again, the expectations here are 35, 2, and 42. So that I don't have to write all that stuff out. Right? 35, 2, 42. Or 35, 42, right? Cool. All right, what else would you want from this implementation?
Did you want to figure out like what the index of the top was?
Index, what's an index?
Or like the, you want to figure out what was at the one at the end?
Yeah, do I want to know that? No. Understand where I'm asking that. I'm outside the class now. Right? Do I need to know something like that? Should I know something like that? That's a leaky abstraction, right? That's not something you should worry about, man. Right? Like, now I'm the stack. I'll take care of that. Don't worry about that. You're pushing and you're popping, right? And I can tell you whether or not I'm empty. I can tell you maybe whether or not I'm full. Is full. That's a variation, right? Remember this variation over here, the call stack, it can be full. Right? What happens when it's full and you try to push something onto it? Stack overflow, exception, no operation, whatever, right? That's another variation. Now, do we have to worry about that necessarily over here in Java? If it's full, then that means that you kind of ran out of memory. So you got bigger problems than that, right? You ran out of the gigs and gigs and gigs of memory that you should have, right? All right, but that is a variation. Right? Otherwise, it looks pretty darn good. What if we had made a mistake and naively said that the top was now not the end, instead it was the beginning? Let's see, what is this? Yep, we add it at index 0 and we add the element. Right? That means down here, instead of removing the element at that last one, we remove the element at the first. Right? We're going to stick with your array-based list here. Right? Now, I don't want to just push all of those elements. I'm going to say stack.for int I equals 0, I is less than n, I plus plus, and stack.add, or not, push, excuse me, I. There we go. And then I'll pop them all off. Right? Let's go ahead and parameterize it so that n is, say, 100. No big deal. Right? It's going to go 99 down to 0, as expected. Right? 10,000. Also instantaneous. Right? I'm not even going to print them out anymore. I'm just going to say stack.pop. There we go. And there we go. Well, I was doing this right? Yeah, because we push 0, 1, 2, 3, 4. Yep, it still works. 10,000 instantaneous. Let me print something out when we're done. System.out.println. Done popping. All right, there we go. Got to be careful on that spelling. Done pushing. There we go. There. Pretty quick for 10,000. Let's go up to 1 million. Is that 1 million? Nope, that's 100,000, 1 million. It's not even done pushing yet. I've counted 10 seconds so far. We'll go 10 more seconds here and see if it gets done. Is 1 million a lot? Well, I mean, in the grand scheme of things, like there's only 4 megabytes, right? Why is it having such trouble with 4 megabytes? It's shifting everything. Let's come back over here and say, okay, what if instead of an array list, I had a linked list? Done. 1 million elements, right? Because it never had to shift anything. So do you remember that quote that I keep giving you, right? You can program every day of your life for 10 years and become a world-class programmer or developer, software engineer, data scientist, whatever you want to call yourself. Or you can program every day of your life for 2 years and take a data structures and algorithms course. Because that one line makes the difference between instantaneous and hours or days or weeks of processing, right? Array or linked, right? And knowing when to use the difference, knowing the difference and when to use one and when not to use the other, and knowing how to properly use one versus properly use the other, that makes all the difference, right? Do I have? I don't have the comic anymore, but there was another one. There was another example of this. Darn it! I don't know. I don't want to waste time trying to find it, but online comic programming database indexes. Please tell me that it's here. Grand Scheme Comics? No. No. I wish I could find it. Nope. All right. Anyway, it's one guy saying, one inexperienced programmer saying, our database is way too slow. It's taking weeks to run these queries. We've got to upgrade to the latest NoSQL, right? Another buzzword. And I've already planned out weeks of training. It's going to take another couple of months to migrate away from MySQL and relational databases into this NoSQL MongoDB. While he's talking, while the other programmer is sitting there going, "What?" Because he knows when to call BS. And so he starts taking a look at his database design. And he goes, "Here's the problem. You don't have any indexes." Done. Right? Puts on indexes, and everything is now lightning fast. Right? What is an index? It's sorting, right? And you've sorted the elements in your table so that you can exploit binary search, right? And in case you think that that's just a comic, no, I've encountered that at least 3 times in my professional life. Man, this is taking forever. It's so slow. I go, okay, do you have an index on that column? What's an index? Okay, we're going to teach you something today here, right? And they're going to teach you how to put an index on this, and we're going to show you it wasn't slow, right? It was that you didn't have the proper index on the column, right? Versus something like this. My immediate thought are you using a linked list or an array list or something, or what data structure are you using? What's a data structure? Okay, now I know what the problem is. Let's go into this. Right? Another example that you'll appreciate from C. When I was a grad student, this guy was just wandering around our offices one day. He was another grad student, but he was from physics. And he was trying, I've been working on this problem for weeks. Please, is there somebody here that can help me? I go, what? Because I don't know any physics. I'm not going to be able to tell you the convolution of your quantum system. What? No, he just pulls out his laptop and he says, I've been trying to crunch these numbers, and I think he was just adding numbers or something like that together. For some actual physics research project. And now this is the C he had. It was like double array is equal to double, and then he had 1, 2, 1, 2, 3, 1, 2, 3, right? And he compiled it. Obviously, this is not C, so it won't compile that way, but you get the idea. And it would compile, and it'd always crash. Well, you tell me, having only taken Computer Science 1, why did it crash? How many bytes in a double? 8. And how many did I just do? 10 million. So 80 million bytes. Is that going to fit in your stack? No. All I did was take one look at his first line of code, and I said, well, okay, here we go. It was C++, actually. And so I did something like this, and it immediately ran. And he goes, "Oh my God, what did you do?" Like, well, I mean, do you have a half hour to sit and tell me to learn about the difference between the stack and the heap and how memory works? And he goes, he wasn't interested in that. He got it working, and he went back to his advisor. So that's why we get paid the big bucks. Another example, more recent, I've got a colleague in civil engineering, and they were trying to reverse engineer a bunch of XML that was proprietary. I think it was like some structural engineering program that had produced this data file, and they didn't want to pay for it anymore. And so he goes, "Can you decipher this data file?" It was just XML, but they had these numbers here that were encrypted. Right? It looked like this. Oh, not Z, but there we go. There. It looks like something like, it looks like it's encrypted. No, it's not encrypted. I just put this into it was actually them, they did try to obfuscate it. They put it in what's called big endian. So they took single bytes or they took single words and then they flipped them. That's what big endian is. It's flipping words. And ultimately I just said, okay, well, I decoded it using reversing the big endianness, and then I said, well, it looks like a IEEE 754 floating point number. And I go, and then I decrypted it, and all I did was convert it back to decimal. And I said, does the number 150 make any sense to you? It is not the same number, but and he goes, yeah, that building is 150 feet tall or something. I go, okay, well, there you go. There's your answer. All they were doing was dumping the hex code using big endian into this XML file. Wow, we don't have to pay them $500 anymore. They could then decrypt all of their data that they had exported in that program. Yeah.
Did you ask for $500?
I should have. There are always stories like this, like the one guy that retired at the factory, and they said, thank you, and then the machine that he had tended for 50 years broke, and they go, nobody knew how to fix it. And so they called him up and they said, could you come in and help us out here? And so he comes in, takes one look at the machine, goes, fiddles with 2 switches or something like that, and tightens this up. And that's magically working again. He goes, oh, thank you. How much? We really, we know you're retired, but we'd really like to pay you what your time was worth. And he goes, oh, okay, I'll send you a bill. And so they send him a bill, and it's for like $1,000 or something outrageous. And they go, that's way too much. You were only in here for like 5 seconds. And he goes, yeah. It was $1 for the 5 seconds, and it was $999 for the experience. So little adages like that all over, old people will tell you these old yarns or whatever. Right? I'm getting there maybe. Right? But anyway, so instantaneous, right? All right. What about the other cousin to this, which are queues? Right? So you may or may not watch a lot of British shows, Doctor Who or whatever, but tell me what a queue is if you have seen British shows.
It's like
Yeah, you're waiting for something. It's a line, right? So you're at the bank. Here's the teller over here. Right? You queue up. You get into a line. It looks something like this, right? There's the teller. Where do you jump ahead? There are a bunch of people in line already, right? Do you get to jump to the head of the line right there to be served next? Nah. Oh, sorry. I'm sorry. There's the teller over here, all right? And it's a line, right? And we've got people waiting in line already. Do you get to jump to the head of the line? No. Where do you queue up? Where do you go? You go to the back of the line, right? We call this NQ, right? And queues are spelled Q-U-E-U-E, right? Right? Not Q as in give me a Q, right? Not Q as in the letter, but it does start with that, so think of it in terms of that, right? This is where the next person gets served. So this is called dequeuing, all right? All right, so let's go ahead and look at that same example with 42, 2, and 35. If I have 42 here, then I NQ it, then I'm going to go and put it here, and they get to go to the front of the line. Now, maybe they have to wait for service because somebody else is already there, right? But now I'm going to go ahead and NQ2. Right? And I'm going to move that to the head of the line, or to the next, right? And then finally, what was it, 35? Justin Steele. There we go. On the IL, but the Cubs ace. Right, there we go. So people are lining up now. Now, the order that I went in here, the NQ order, right, NQ order, is going to be 42, 2, and 35. What is the DQ order? 42 gets served next. Everybody moves up. Oops, not the line, but there we go. Everybody moves up. Who gets served next? 2. Everybody moves up. And then 35 is served next. Tell me about those two orders. Exactly the same. This is called FIFO. First in, first out. There are these nice little acronyms all over. TITO and GIGO. You've probably heard of GIGO before. Garbage in, garbage out, right? No, you've never heard of that? And then the opposite is going to be treasure in, treasure out, right? So what you really want is garbage in, treasure out, right? You want to spin gold, right? You definitely don't want the other one, TIGO, trash in, garbage out, or sorry, not trash, but treasure in, garbage out, because that means that you've ruined things, right? So if you've ever heard of these acronyms, TITO, GIGO, and whatever, right? But this is FIFO, or first in, first out, because the NQing order matches the DQing order, right? It's a line, right? Why do we call it a queue instead of a line? I don't know, maybe the first person to talk about these as data structures was Brit. Who knows? But that's what the Brits call lines. Right? It's a first in, first out data structure. Right? We do not generally allow line jumping. There are variations that do allow line jumping. They're called priority queues. Right? The most famous, I've never been to Disney. I have been to Disney World, but not since I was a small child, right? But apparently in Disney World, you can pay for the express pass, right? If you're rich enough, you can go ahead and pay for this express pass, and you can jump ahead of the line, right? The problem is lots of people pay for those express passes, and so it's just a smaller line, right? That you're still waiting in line for. But we're not going to allow line jumping until we get to priority queues. Right? Again, it is a restricted access data structure. We're only going to allow you to NQ things or DQ things. We insert something from the end of the queue or the front of the line or whatever, right? And we remove something from the front of the line. Right? Front, back, usually go back to this one. This is the front of the line, right? Because line jumping would mean, oh, yes, sir, you're a very important person. Go ahead and jump to the front of the line, right? Or get to the back of the line, right? Because you're not as important, right? So NQ over here. Right? So front and back of lines. Right? Same exact considerations as before, right? How are we going to implement these things? Let's come over here and let's go ahead and create a class called queue. There we go. I'm going to do it with a list, just like somebody just suggested there. But what kind of a list? Yeah, why did you immediately jump to a linked list? Yeah, you need to work from both ends, right? And granted, if you use an array-based list, then this will be efficient over here, but then the other one is always shifting it down, right? So one of those operations will be efficient, but the other one necessarily won't be. So in this case, I definitely want a linked list. Let's go ahead and design those public methods. Public, void enqueue, right? T element. Right? Public, void, I guess it's not abstract, so let's go ahead and actually do it. Enqueue elements dot add element, right? There we go. So where am I adding it? I'm adding it to the end. So I'll put that in a note here, adds to the end. All right, dot, dot, dot. And so down here, when I return something that I dequeue, then I need to return elements dot add, or not add, dot remove. Where do I remove? At the start, right? So removes from the start. All right. Let's come over here and change this in our demo. Here we go. So stat queue, queue, and queue. Right. And let's go, I don't want that. Let's just go with 10. Right. And my queue here is going to be an enqueue. Right. Done enqueuing. There we go. And while the queue is not empty, I will say queue dot dequeue. And I'll put that into my print statement here so that I can see that things are coming out in the proper order. It's done dequeuing. I don't even know if there's proper words or spellings or whatever. All right, so hey, is empty. Let's go ahead and put that in our queue implementation because it seems like it's so, useful. Public Boolean is empty. Return this dot elements dot is empty. I've repeated some code there. Right? Maybe I can look for ways to reduce that, right? Between stack and queue. Right? And let's go ahead and run this. So done enqueuing. How are they going to come out if I, uh-oh. 13579. Oops. Enqueue. Oh, sorry. I doubled it. I don't want that. There we go. There. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The order that they went in my for loop up here, is the order that they came out down here. Okay? Now, is a stack a queue? Is a queue a stack? Neither one of those seems correct. But both of them have this function here. Maybe I could put that into an interface that says, is fillable, is emptyable, I don't know, something like that, right? So that there's some commonality between those two things. That's probably a Yagni, so I'm not even going to do that. But what happened? What would happen if you tried to dequeue from an empty queue? This queue is empty. So what does the teller do? The teller is up here trying to serve customers. They take a break. Yeah. They do other things. They twiddle their thumbs. They don't sit there yelling out next, 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 next when the line is clearly empty. Right? That'd be really annoying. We don't want that. That's called busy polling, right? Is there anybody there? No. Is there anybody there? Is there anybody there? Over and over and over again. Instead, now this is not a person, but yeah, you're right. They take a break. What we do is we take this program or we take this operation or whatever, and we put them to sleep. Right? Go to sleep. We'll wake you up. Literally, this is what we do. We put that to sleep, and we'll wake you up when somebody is in this queue. Right? So that gets into PDC concepts, parallel and distributed computing, which we won't get into here. But I've got my queue. Great. Some other secondary functionality, sorry. Secondary functionality. For both of them. You can have what's called a peek operation, right? View, in other words, return, the element that would be popped or dequeued next, but do not remove it, right? That's why we call it peek. You can peek into the, like, here's your stack. What is on the top of the stack? All right, I'm just going to peek, but I don't want to remove it yet because I want to see what it is. Right? Should you be able to peek at anything? Probably not, because that's not a stack. Right? You can have what else? You could support a maximum capacity, right? For either or both, right? You'd probably want an is full, right? Or get remaining capacity, right? Et cetera. Right? And a lot of times you do want to put on a capacity. For example, one application of a queue is a buffer, right? You don't want a gigantic buffer. Instead, you want it, once the buffer is filled, you put that thing to sleep. Say, nope, the buffer is full. You can't do anything until we take care of what's in the buffer already. And you do want a maximum capacity there because you don't want just the buffer to grow without bounds. Otherwise, you'll run out of memory or something. Or it means that data is coming in faster than it can be processed, which is a problem in and of itself. Right? So other considerations, again, what happens when you push or enqueue on a full stack or queue? What happens when you pop or dequeue from an empty stack or queue, right? You have to think about those things. Are we going to throw an exception? Are we going to return a flag value like null? Are we going to have it be no operation, et cetera? Okay. There are other variations on this. So here's one variation. In practice, you can use what's called a DEQ, right? DEQUE, and it's just pronounced deck, right? Like you know, your backyard deck, right? And what this is a doubly ended queue, double-ended queue, right? What it is you can add or remove from both ends. Right? This allows you to use any combination of push, pop, or enqueue, dequeue. Right? DQUEUE, right? So here's one particular application of this. Let me come over here. Right? All right, so take a Word document. You type. That's an operation, right? Type. That's a second operation. You copy and paste. That's the third operation, right? You're keeping track of these operations because maybe you want to support an undo operation. So operation 1, operation 2, operation 3, right? You went in this order. If you do undo now, right? Control Z, that's well known, right? Everybody knows Control Z. That'll work in most programs. It undoes the last operation that you did. Well, how are you keeping track of that? Presumably in some sort of a stack. Why? Because you look at the top of the stack and you say, oh, well, that was the last operation to be done. So if you go Control Z, that's the operation that I undo, right? But you don't, and so when you do a new operation, what happens? You put it on the top. When you undo an operation, you pull it off the top, right? Because undo, right? You want to go in the reverse order. You want to keep track of breadcrumbs, just like Hansel and Gretel going through the forest here. There's a breadcrumb, there's a breadcrumb, there's a breadcrumb. How did you get there? Well, all you have to do is follow your breadcrumbs back to see where you came from. But there is a limit. If you open up a Word document and you are working on it for hours and hours and hours and doing a million operations, right? Eventually what's going to happen to this stack? It fills up, right? But we don't want to just say, okay, nope, Stack Overflow, right? Because if you ever experienced that, you've done too many operations in Word and it says, nope, sorry, the operation stack is now full, so it would mean that you can't undo anything, so we're going to stop now, right? User-focused applications like word processors don't do that, right? Because the user would not understand what the hell that means. So what we do is we have a bottomed-out stack here. There we go. So that when this gets filled up, what happens is I'm going to go ahead and fill this up, and we've got now another operation here. We don't want to lose anything in this sequence. What we'll lose is the oldest operation, and it gets popped off of the bottom of the stack. That only is possible if you are able to do two operations at one end and another third operation at the other end. Right? This is a perfect example of when to use a deck. Right? Okay, here's another example, but with a queue. Right? Now we are going to allow VIPs at Disney World. People come in and we NQ things here. We usually DQ things over here, but guess what? We've got a very special person coming in, right? They've paid $1 million to be able to jump into the head of any line, right? So this VIP person comes in and is able to jump the line, right? Now, in case you think, oh, no, we don't want to support that because we want to be fair. Well, no, you don't want to be fair in computing because there are some things that should be jumping the line. For example, an operating system. It runs user applications like your Spotify and whatever I'm doing over here, Eclipse or whatever, right? But there are more important things for an operating system to do. Reclaiming memory, making sure that the operating system is doing something, right? So operating system operations, they get to jump to the head of the line because they are the most important. Otherwise, if the operating system doesn't operate, then the user stuff can't operate. And so often you will have programs that are able to jump to the head of the line. Yeah?
Would this be like a system data?
Yeah, something like that, exactly. Or something with a really low priority would be like a database backup, right? And you can actually be, that's too big. You can actually be nice about it. Right? So if I go, I don't want to be over here on my system. I want to go on to some other system. Here's the system that we use for grading. If I go, HTOP, let's go HTOP. Nice and pretty. Oh, come on, HTOP works. There we go. Looks like we've got 48 cores running on that system, right? Numbered 0 through 47 here. And it looks like a whole bunch of memory is being used. It's actually 135 gigs of only 251 physical gigs are being used. That's RAM. There's the swapping memory. Where is our actual percentage here? I'm not seeing an actual percentage of. But anyway, some of these things don't matter. Like whoever the hell that is, that's a user. They're using something. But NX is probably a daemon. Yeah, in fact, it is a daemon there, right? So it is. It's running some sort of NX server there. NX server is probably somebody's remoting into this the server here using NX and Pokemon.py, and it's somebody's editing a Python program to edit their Pokemon program, right? What?
Is that in Vim?
Yeah, that's VI. Well, it's a non graphical Vim, yeah, and so kudos to them for using VI, right? Whoever that is. But otherwise, and there I am at the top there using HTOP, right? But there are, system level processes that should shove those user level processes out. In fact, you can run something, say, I don't know,
Neofetch.
do what?
Neofetch.
What's that?
It just fetches your system's specs.
Oh, NeoFetch?
Yeah.
That sounds like it's not.
Yeah, you can install it.
Yeah, okay. So, PS? Yeah. PS is just listing all of my processes. PS all is listing all the processes, right? And so what you can do is when you launch a program, say, is there any long-running program that I can launch in the background here? I know. Tail F foo. There we go. All right, there are no changes to that, whatever's in that file there. So it's now I'm going to go ahead and run it in the background, right? There. It's running in the background, waiting for somebody to actually change that file, and then it will print out that change. And so obviously it's not using that much memory here. In fact, it's asleep because there are no changes. But what you can do is you can run. So let's go ahead and kill it. 8697. There we go. And now it's dead. But what you can do is you can do something called nice, right? Yes, right? run a program with a modified scheduling priority, right? You can be nice about it, right? I can say, no, my program is a very low priority. I'll run it with a niceness level of, say, 20, positive 20, or 19, I guess, is least favorable to the processor, right? Versus, no, I'm not going to be nice at all. I'm going to shove my way to the front of the line, right? By saying that, no, this needs to run at negative 20. Now, that's only with respect to other user processes. That doesn't mean that you're going to jump, that if the operating system comes in and jumps ahead of the line, to the head of the line, that, no, I get priority just because I was not being nice, right? Because the operating system comes first. So this kind of scheduling stuff is done using a queue, and obviously there's some sort of priority here because some processes are way more important. Like whatever the operating system is doing is way more important than that guy editing up his Pokemon Python script, right? So there's another use case for using a deck. You want to do multiple operations at both ends, okay? We'll look at a couple more variations and wrap it up with lists and list-based data structures on Tuesday. Right? Otherwise, I'll see you up in lab today.